Hello and welcome. We'll keep going here. I always like to kind of take a few seconds to get before we get going. Just kind of hang out for a moment. Yet again, praise God for the day. I'm grateful, you know. I want to continue on the next problem, next question. Just keep it going. Just keep going. So, delete a node in a BST. So let's see how this goes. I don't know. BST isn't necessarily balanced binary search tree, so it may not necessarily be a particularly hard question. Search for node, remove, delete the node. This might be kind of easy. Oh, hide the tree. Yeah. Okay. I think this is a relatively easy one. Yeah. This should actually be really straightforward. Hopefully I don't mess it up. This should be like a few minutes if I'm not. This is like kind of a standard thing. Like kind of one of the easier questions, I think. This probably shouldn't be a medium. This probably should be an easy. But let's see how this goes. So we'll say node P, start off at the root. So while root not equal to key, oh no, while root and root, or no, excuse me, P, and P is not equal to P value rather. Now, is the key always going to be there though? That's the question. Okay, sure. Yeah, well, if the key's not there, then I think we don't do anything, right? I think we just return. Oh, excuse me. What if you? Oh no. Oh, I see. Okay. Actually, the deletion itself is the thing that's finding the node is not. Oh, I see. Okay. Never mind. No, this is a little more involved. Okay. Maybe it's not that easy. Find the appropriate node first. So we'll say if key is greater than p value, then we're going to say p is p. So if the key is larger than this value at the head, we're going to go to the right. Otherwise, we're going to the left. Okay. Now, if not p, edge case, key, the node containing the key wasn't found. Okay. Okay, we'll just handle that case on its own. The tricky part here is that this node that we're going to remove, it could have subtrees. And if it has subtrees, what do we do? Right? It could potentially have a left subtree and a right subtree. You can shift the right subtree to where it was, but what if the right subtree has the left subtree? Where are you supposed to put the left node? I want to say actually this left subtree should become a subtree of your right tree. And the right tree should become the head node. So what you're going to do is append the left subtree on the leftmost node of the right subtree. Hopefully that makes sense. So hopefully they give an example. They don't. That's awkward. I think, yeah, okay, this is a little bit harder than an easy. If it's right, even I could be just wrong too, which would, yeah. So remove, and then a given node and replace it the right subtree. Shift the left subtree to the leftmost node of the right subtree. Order to maintain the BST status. Note, this is not the BST, so we do not worry about balancing the tree. Okay, so we even need to know the parent of P, don't we? Oh boy. Okay. So set parent to P, and update P. Indeed. And we need to know also if this is the left subtree or the right subtree. Okay. So left, I guess we'll start with true. Hopefully this makes some sense. Hopefully this works. Okay. Yeah, we didn't really consider how do we erase that node? How do we remove it altogether? Also, we have another edge case if the parent is a yet another, if the root node contains the key. All right. So this is not an easy. I'll give it a medium rating too. I'll probably make a mistake. Excuse me. It's more than possible that I'll make a mistake here. Okay, so. Okay. It's P left. Right. Say if the parent exists, then we're going to say parent. Now we're going to say if left, else. So if this node is a left child, then the parent left is going to be rewritten to the right subtree. If this is on the right side, parent right is going to be rewritten to the right subtree. Alright, so we're looking at this picture before, but it doesn't matter if it could be on the other side too. In this picture, we would want the right subtree to move over, the left subtree to become the subtree of this node. If there is no parent, then I guess we don't perform this at all. I guess it doesn't matter. Yeah, I don't think it matters if there's no parent. Just thinking, the parent should actually start off as a null pointer then. Yeah, then the left subtree just becomes a subtree of the right subtree. Simple as that. Locate the leftmost of the right subtree. if it exists. There's another issue here where what if the right subtree doesn't even exist, right? These cases it exists. If the right subtree doesn't even exist, then actually, let's do that first then. Because if it doesn't exist, then actually we should update this node to we'll call this the new node rather than left and right. So let's do it this way. New node or new node. Yeah, call it new node or new position. Yeah, okay. I want to call it like replacement node or something. Like RPL node. Just call it new node. That's fine. It's not really a new node though. We'll just call it replace node. We'll keep it a long name. That's fine. Okay, the leftmost node of the right subtree if it exists. So if right, then leftmost equals right, and we're going to say for previous is null pointer, and then we'll say this actually. So we actually this replace node we'll set it see it could be the we'll start it off as the left node, right? There is no right node at all, then it just defaults to the left node, whatever that is. That could be a null pointer as well. The leftmost we're going to say is the right side, and then the previous is a null pointer, and we're going to say while leftmost. Then we're going to set previous equal to leftmost, and leftmost, left. Right? So go to the right subtree and keep moving down the leftmost until this is basically gone. We'll just call temp, it's better. Temp, and then leftmost. It's probably better to do it this way. Gotta be careful renaming variables though, it gets confusing. So yeah, so this will track all the way down. The temp variable will become a null pointer, but the leftmost will be the sort of last node before it's empty, before it's null. Excuse me, forgive me for coughing on the microphone. I'm doing so much coughing and talking that I'm thinking it's hard for me to keep it all together. Also, it looks like we're 15 minutes in. Okay. So if you have a right subtree, you're going to do this, and then once you've done that, then you're going to set this replace node equal to this leftmost node, and then now you're going to say this. Oh no, excuse me. Sorry, this replace node, if there is a right node, it's going to be set to the right side. And you're also going to say yeah, you're going to set this replace node to the right side, and you're going to set the right node's left node, or really better would be the replace node. It should exist, it does exist. You're going to say, really it's going to be this leftmost node on the left side is now going to be RP left. Yeah, okay, hopefully that makes sense. So now we've taken our our left subtree and moved it to the bottom of the left side of the leftmost node of the right subtree. And we also want to take our key, our node, the node we found, and set that the left side to be a null pointer, right? We're going to remove this node anyway. It doesn't really matter, but I guess it's somewhat meaningful here. Excuse me. If it exists, and move the left subtree of our target node to the right, to the left side right subtree. Again, if it exists. Alright, kind of convoluted. Now our parent node, we want to remove P. If the parent exists, move P by rewriting appropriate child node to the child pointer to the replacement node above. So actually, excuse me, this is now that replace node. So I just want to make sure we have the right, so this defaults to the left side. If there's no right side, then it'll stay the left side, right? We delete the node, you just move that up. Should be fine. However, if there's no right side, there is a right side. However, that left side gets moved to the right side, and then you actually move that replacement, which is the right side, up. And then we delete the free the memory for the removed node. So we should set I guess we don't really need to change this here quite. We don't really need to do that. Can actually do this. I rarely use this double equals in one line, but I think you can do it here. We don't want to delete anything in our new tree here. Technically we should delete this. And then return, now here's the tricky thing. If this was the root node, actually, before you do that, determine the new root. If P equals root, then we actually have to set ret equal to this replace node. Return ret. Okay. Alright. Kind of involved. A lot of kind of, I guess, edge cases. I don't know if this compiles. Wait, what's wrong with this? We'll just say left child or key is left child, something like that. Again, you have to be careful when you replace variables. Key node, target node. I don't really like long names, but every now and then it's fine. It's appropriate. The work works out okay. Uh-huh. Oh, it worked. No kidding. Really. Wow. What? We have to go through each of these test cases, though. And not just the cases they gave here. There's like quite a few different edge cases here we have to look at. Invalid test case. Nice. So somebody's giving me a call. I don't know why. Alright, so how are we doing on time? Okay, we're a little bit over on time. Kind of want to have this done in like 15 minutes, something like this. So, and this is way more complicated, by the way, if you had to rebalance the tree. So we're kind of lucky. This actually is like an easier question. So part of the issue is if this is the root, there's a replacement node. Let's just try like if there's a left subtree, if there's a right subtree. So say 1, 1, 1, 2, delete 1, 1, 2, 3, delete 1. What do these look like? Valid test case. Oh. Wait, what do we do? I think this is 0, 1, something like this. Whoops. Oh, okay, I made a mistake. True root is not a BST. Which one of these is giving me a hard time? Okay. It's probably this one. Okay. What is going on? Hello? Okay. What's that? That was weird. I don't know why that took so long to sort out. So these are not BSTs, is that what they're telling me? 2, 1 maybe? Something like this? I don't know. Yeah, what do these trees look like? Okay. Can we... Okay, let's go back. Put those there. Delete this. Visualize this. Okay. Alright. Oh, I see. Okay. I have to keep it on the one on top. Alright, so we want, excuse me, 1, 2, 1. What does 1, 2 look like? Null. Okay, I wanted something like this. I wanted 2, 1. Delete 2. And then I wanted the other one, which is, what does that look like? Wait, hold on. 1, 2, delete 1. 2, 1, delete 2, and then 1, 3, delete 2. These cases. Okay. And then now if we attach to 1 on this guy, well, actually I think we probably got all the cases then if these work. Probably. There's I think one more case that I'm missing and or haven't considered. It's like one issue, which is if it's a root node, there's no parent. Okay, so let's say we're not operating on the parent node, or rather we're not operating on the root node. We just want to figure out, right, is it a left child or a right child? Got that. And obviously, if we don't find the key, then we're done. So we find the key, and the parent exists. So there's some replacement node that we want. This works, right? That's fine. We can easily figure out the right replacement. And then it depends if there are no children. There could be one child. There could be no children. If there are no children, the replacement node should just be the null pointer, which will take p left, which is a null pointer. This won't go anywhere, and that'll work. That'll be fine. If there are, excuse me, if there's only left child, there's no right child, this doesn't do anything. Again, this is left child, and then we get the left child in the right spot, which is good. If there is a right node and not a left node, right? We say the replace is left, so left, but there is a right node. Then our replacement is going to be that right node, and so that gets set properly as well. If there is a left node and a right node, then we said the left node is going to get placed onto the leftmost node. Now, if there's no left node, then this leftmost left on the right subtree, right, doesn't matter what p left is. We're gonna, if it's the null pointer or whatever it is, doesn't matter. That'll get tacked on the left side of the right subtree if there is a right subtree. So whether or not there's a node on the left side doesn't matter. If there's a right node, it's going to get tacked. Whatever's there is going to get tacked on the right side. Okay, I think all those cases are handled properly. Now, are they all still handled properly if we're at the root node? So that's the question. If we're at the root node, there's no parent. That means always the left subtree, if it exists, is going to get tacked on the right side, which is going to happen regardless if we have a parent or not, if a root node or not. And then the replacement node is basically what the root's going to point to, more or less. And the replacement node is always going to be the left side, or actually really should always be the right side. But if there is no right side, then it should be the left side. If there is a right side, though, then it'll be the right side. So I think that works even if there's no parent. Yeah. And I think this is correct, actually. In all, I want to say no. I'm afraid to say all cases, but I think it's right. Hey, you got there. Sweet. Nice. How long did that take? Almost 30 minutes. All right. Not great. Not great. Not the most efficient either. Really, rather inefficient. Used a bit of memory too. So apparently there's a more efficient way to do this, but I don't know. I thought this was okay. I mean, this is, I guess, I actually don't know. Let's try again. Okay, there we go. Okay, it's kind of random. All right, that's much better. Yeah, there we go. Sometimes you roll poorly. All right, almost 80%, 90%, what have you. That's pretty good. All right, so thanks for watching. I will talk to you soon. And yeah, that's how you delete. Now, that's a much more interesting question is if it's a balanced binary search tree, then you've got to get into node rotating. If it's like an AVL tree or what do they call that? An AVL tree or a red-black tree or something of that nature. Which, by the way, if it's balanced, it's not necessarily a, what do they call that? A complete tree, I want to say. Not necessarily a complete tree. Or is it complete? Or is it full? Either full or complete. I can't remember which one, what the term is. But meaning the height of the tree is not necessarily like the absolute logarithm plus or minus 1. I guess logarithm of the number of nodes plus or minus 1. It's a balanced binary search tree is height balanced, meaning it's the height is logarithmic with respect to the number of nodes in all depths, but it's not exact. It's not like very close, if that makes sense. It's not like within 1 or 2 nodes of the depth. It's like a multiplicative factor within the logarithm of the number of nodes. That's the depth, which is very different than what I used to think or used to understand. So that was kind of a new revelation for me, which is like, I don't know if that's a good thing, but yeah, we didn't have to get into any node rotating here, so that was nice. But pretty interesting question. It should be a relatively easy one. Kind of one you should be able to do in like 15 minutes, but obviously there's like quite a bit of like different cases that you'd want to consider. So it was a bit challenging for me. So yeah, thanks for watching. Talk to you soon. Have a good rest of your day. Take care.